Welcome to Study Loop.
Hey guys, let's do problem 50. The first question is we need to calculate the volumetric flow rate. It is given that the input volume is at STP. Therefore, 1 kilomole of gas occupies (22.4 meter cube), and the number of moles of gas is that is getting in is the volume that's getting in, which is 3.74 given in the problem, divided by 22.4 meter cube per kilomole. Therefore, the number of moles of gas is 0.167 kilomole per minute. It means that each minute 0.167 kilomole gas is getting in. Given the feed gas contains 22 mole percentage of DSC, DCS, and 60% of the DCS has reacted. Therefore, the moles of DCS reacted is equal to the 60% what is reacted, which means 0.6 multiplied by the mole fraction of DCS and the total number of moles that was fed, and therefore 0.6 multiplied by 0.22, that is the mole fraction of DCS, multiplied by the total number of moles, which is 0.167 kilomole per minute. And from here we get the moles of DCS reacted is 0.022 kilomole per minute. Since 2 moles of nitrous oxide reacts with 1 mole of DCS, therefore the number of mole of nitrous oxide is the number of moles of nitrous oxide at that point which reacted is 2 multiplied by the number of moles of DCS that reacted, which means that 2 multiplied by 0.022 or 0.044 kilomole per minute. Therefore, the amount of unreacted nitrous oxide, let us calculate that. That is equal to the mole fraction of nitrous oxide multiplied by the number of moles that was fed minus the number of moles of nitrous oxide which reacted. Let us insert the values. The mole fraction is 0.78. The total moles is 0.167 mole per kilomole per minute. minus 0.044 kilomole per minute. From here we get the amount of unreacted nitrous oxide is 0.0863 kilomole per minute. Similarly, the amount of unreacted DCS is the percentage of DCS multiplied by the total number of moles minus the amount of DCS that reacted. From here we get the amount of unreacted DCS is 0.0147 kilomole per minute. Since each mole of nitrous oxide reacted, it creates 1 mole of nitrogen and hydrochloric acid. 1 mole of nitrous oxide produces 1 mole of nitrogen and 1 mole of hydrochloric acid. Therefore, the number of mole of nitrogen and hydrochloric acid at point A are the same as the number of moles of nitrous oxide at point A. And the number of moles of hydrochloric acid at point A is equal to the number of mole of nitrous oxide which reacted, which is 0.044 kilomole per minute. Now we can calculate the total number of gas. Let's do that. Therefore, the total number of moles of gas at point A it is the summation of the moles of all gases at point A the number of moles of DCS at point A plus the number of moles of nitrous oxide at point A plus number of moles of nitrogen at point A plus the number of moles of hydrochloric acid at point A. Therefore, we can do the summation here. Therefore, the total number of moles of gas at point A is 0.189 multiplied by 10 inverse 3 mole per minute. We get kilomole. Let's convert it to mole. Mole per minute. Therefore, we can calculate the volume of gas as nRT divided by P. Number of moles is 0.189 multiplied by 10 inverse 3 mole per minute. Gas constant is 62.36 multiplied by 10 inverse 3 meter cube torr, mole inverse 1, Kelvin inverse 1, and the temperature given is 900 degrees Celsius or 900 plus 273 Kelvin. Pressure given here is 604 millitorr or 604 multiplied by 10 inverse 3 torr. When we do this calculation, we get 2.29 multiplied by 10 to the power 4 meter cube per minute as the volumetric flow rate. The next problem says, what is the rate of deposition? Let's calculate the rate of deposition. The partial pressure of DCS can be calculated. The partial pressure of DCS is equal to the mole fraction of DCS at point A multiplied by the total pressure, and the mole fraction can be found by dividing the number of moles of DCS at point A divided by the number of moles of gas at point A multiplied by the total pressure. The number of moles of DCS at point A is 0.0147 kilomole per minute, and total amount of gas at point A is 0.189 kilomole per minute. The pressure is 604 millitorr. Therefore, the partial pressure of DCS is 47.0 millitorr. Similarly, the partial pressure of nitrous oxide Therefore, the partial pressure of nitrous oxide is 276 millitorr. Now, the rate of deposition. The relation is provided for the rate of deposition. The equation is R is equal to 3.16 multiplied by 10 inverse 4 the partial pressure of DCS multiplied by the partial pressure of nitrous oxide to the power 0.65. So we have all these values here. Let us insert that. The partial pressure of DCS is 47 and the partial pressure of nitrous oxide is 276. Once we do that calculation, we get the rate of deposition is 5.73 multiplied by 10 inverse 5. And finally, how thick is the silicon dioxide layer? Question C. From the rate of deposition, we can calculate the moles of silicon dioxide deposited after 2 hours. From the rate of deposition, we can calculate the moles of silicon dioxide deposited after 2 hours. Therefore, the thickness can be calculated as the molar mass of silicon dioxide is 60 kg in 60 multiplied by 10 inverse 3 kg per mole. The specific gravity is given 2.25 and the density of water is 10 kg per meter cube. Once we do this calculation, we will get 1.1 multiplied by 10 inverse 5 meter. Let's convert it to Armstrong. Or 1.1 multiplied by 10 to the power 5 Armstrong is the thickness. Of the silicon dioxide layer, and this thickness would be thicker. The thickness would be thicker toward the entrance of the reactor because the partial pressure of DCS and the nitrous oxide would be higher, resulting in a higher value of the deposition rate. Let's write it down. Resulting in a high value of deposition rate.